everyone. Today we're going to be talking about dual pol radar. So let me start by sharing the screen and get to our PowerPoint. So this is the last part of that section. So when we talk about dual polarization, there's something that you have to understand about light. We always refer to light as being a wave, some sort of electromagnetic wave. The reality is actually a three-dimensional wave. So not only does it go up and down, it's three-dimensional, so it goes across. So it's more like packets going like this. That's what a wave really is. So what we can do is we can polarize it. We can say, let's only look at the light going this way, up and down, or the light looking this way. If you wear polarized sunglasses, this is basically what you do. When you are looking out and you see light, you're seeing reflections, and the light is going in all different directions of that wave. So we're seeing this entire three-dimensional set of waves. Putting on polarized sunglasses will cut all of the waves that are either up or down or sideways. And what that does is it allows for a lot less glare. It's not as bright. You're able to make things a lot more clear. If you really want to take a look at this, go look at a parking lot with a bunch of cars and look at the reflections. Putting on polarized sunglasses makes it so much better. Anybody who knows anything about going on a boat at the waves, which are causing lots of packets of glare, you can almost completely eradicate that glare with polarized sunglasses. So they're expensive. They're a lot more expensive than the cheap sunglasses you can buy at the store, but they're definitely worth it. Well, in any event, up until recently, the radars, even the WSR-88Ds, couldn't tell the difference between what was up and down and what was sideways. And we've been able to improve the hardware, and now we have dual polarization radar. Or if we want to be cool, we call it dual pol. Okay, so we want to think of the radiation as being aligned vertically, and the other is aligned horizontally. Now, the difference between horizontal and vertical reflectivity, capital Z, is what we call differential reflectivity, or ZDR. And we measure it in terms of decibels. So it's the difference between two. We talk about it being dBZs. There's a method. If you go 4 plus 4 dBZs plus 3 dBs is 7 dBZs. Don't worry about that. It's just the difference. So what we're looking at is the horizontal orientation and the vertical representation. So it tells me something about what the structure is of the object that's returning radiation. That's what differential reflectivity is, the difference. So what does a raindrop look like? This first diagram is pretty hilarious, right? This is how people draw raindrops. I don't know where that came from. I don't know if that's a cartoon or advertisement from the 1950s, like Calgon or something. But raindrops do not look like this. They do not have little points on top. What they do is they start as little spheres. But that's only true if the raindrop is really small. As the raindrop becomes larger, bigger than, let's say, 2 millimeters, and especially the bigger raindrops at 5, notice that the air that's coming in there resists and starts to break them up. So they become sort of like this squished spheroid, oblate spheroid. And as the raindrop is falling down, they will eventually break apart into 2 smaller raindrops that then can continue the growth. So what we're saying is that small raindrops are being spherical. The bigger the raindrop, the flatter it is. Okay, and here's a picture of those raindrops. Well, what that does is it says the radiation going up and down is going to see a different raindrop. It's going to be much thinner than it is if it's looking horizontally and seeing a really wide raindrop. And if you remember that reflectivity is proportional to the diameter to the 6th power, right? That's a big difference. Big flat raindrops are going to be really bright when you're looking this way, and they're going to be a lot dimmer if you look up and down. And so when you have a big raindrop like this one over here, 4 millimeters, you're looking at about 4.5 dBs difference. So because we know that, we get an idea of how big those raindrops are. Now, we did in class talking about, I said, if you could just double the amount of raindrops, or if you could just double the size of the raindrops. Well, that's not really how the atmosphere works in reality. In reality, we have what's known as a drop size distribution. And when you take a sample of raindrops in a cloud, there's going to be raindrops of all different sizes. Some of them are going to be huge, some of them are going to be small, some of them are going to be really tiny. So they're all in the process of growing, becoming larger when they bump into each other. It's called collision and coalescence, if you're interested. They become bigger and bigger, but then the wind blows them apart and then they become smaller. So there's this continuum of raindrop sizes, and it's called the distribution. So when a radar looks out, they don't know what exactly that is. It just gives you an idea of how big the signal is. So when we start looking at the differential reflectivity, what we see here is, and let me get my pen, I'm going to use green here. What we see here is when it's rain, that when we go from small ZDR to large ZDR, we're going to much bigger raindrops. So we can use ZDR as a way to say, well, what do I think that raindrop is? We've talked a little bit about classifying those hydrometeors. If you look at hail, right, hail it's kind of roundish, right? So there's a lot of things that we have to be careful of. We may not get the same amount, but we get giant raindrops with ice cores. Well, that might be something different. But for the most part, hail is going to be somewhere in the middle, especially as it's melting, because it's sort of a big sphere a lot of times. Graupel, which is like little snow pellets, somewhat smaller. Snow can get wet and then they look like they're bigger. Ice crystals, clutter. So all this stuff is showing me information. Now, chaff is stuff that you might throw out for a radar to pick up little pieces of metal. Enemy airplanes, when they're being shot at, would release chaff to try to take a missile and decoy it. Debris can be all over the place because the debris can fly this way or it can be this way. So debris is going to be kind of all over the place. But this is just sort of a table that we put together. I don't need you to know that except for the raindrop one, where you just realize that I can get information from differentiating between signals that are going up and down versus horizontally. So when I look here, I can see here's reflectivity in dBz's on the left. Here's ZDR on the right. So when we see areas of higher dBs in terms of ZDR, we might see some larger raindrops. This is what we can look at. We compare the two. Now there's another thing that goes on. It's known as CC, correlation coefficient, or rho HV. I'm not going to be that concerned about this, so you don't have to freak out at this. Just listen to what I have to say. It basically says how consistently does the beam behave? Does the pulse go out? And we can separate horizontal from vertical. One of the things that we want to talk about is this. If I've got a mixture, and you know what, this is not the right diagram. So let me explain what this should be. So we're going to pretend this is right, this is wrong. Oh, sorry, I lied. We're going to pretend that this is wrong. We will have a high CC. Think about it as being consistent. If I have all of one type. So if I look at a cloud and it's all rain or all snow, then the signals will be fairly consistent. If it's all rain or all hail, it's fairly consistent. But what happens if I mix them? If I have some rain and some snow? So here we're going to say this is mixed. I really should fix this picture because I don't know where I got this from. This is not the right thing. This one says it's going to be inconsistent. So think about correlation coefficient as consistency of precipitation. If it's all rain, if it's all snow, it's consistent. High CC. If it's not, low CC. And we can look at this and we say we want to get values closer to 1. Okay, so over here, values closer to 1. Decreasing drop size diversity. Lots of little drops, they're all the same. All small hail, all dry snow, all the same kind of ice crystal. The more different they are, the lower the CC. But they're all going from like 1 to maybe 0.995, right? Almost everything falling is in this area. That might be different when we get giant hail because now we get a different type of scattering. I'm not going to talk about that. Or snow with big wet, remember it's melting, we see some stuff. But what is really important is if you look at this, debris. Notice how much lower debris is. Why is that? Well, if a tornado blows through a house, a subdivision, there's going to be crap flying all over. Do you agree? Some of that will be big 2x4s, plywood. Some of it will be like little fiberglass dust, all sorts of small pieces. So would you agree that when a tornado blows things into the air, it is very low consistency? There's a lot of different sizes and a lot of different shapes of all this stuff. So debris has a low CC. I want you to keep that in mind, okay? So here's what it might look like here. When I'm up near the dark reds or the pinks, then I have fairly high consistency. So I look at all these rain things over here, and this is the same vision on the left with just reflectivity. Over here, it's all the same. When I go further away, it's getting to be a little bit lower CC, which means this is where there might be some rain or snow. Over here, look at that's a pretty good little shower or thunderstorm there. So when we see this low CC, what I'm probably suspecting is that I've got some hail mixed in with that. So that's one of the ways that we can use this. This is all rain or it's all snow. This one's got some mixed precipitation. Now there's a couple other things here. I'm not going to worry about specific differential phase, but if anybody's going on in this, they need to know specific differential phase, which we call KDP. It basically says, depending on the rain or the precipitation, your signal is going to get shifted a little bit. We're not going to talk too much about this. I'm not even going to talk about it with you guys. All I'm going to say is that when I look at values of this, when I get to rain, rain is going to have some really high values. Hail, graupel, snow crystals, and ice crystals are all going to be in this kind of color range. So if I use KDP and I see this color, it could be rain, could be snow, graupel. But if I see these colors, I'm going, that's rain. So I know that because rain does things differently than snow was. It says non-meteorological echoes like insects or debris. It's too noisy and we don't even think about it. We don't even worry about that. So let me show you a picture of that. And here we go. We're looking at all this and you can see at all the little shower cores that we have sort of these higher values of KDP indicating that's all rain in that region. Now, we've talked about algorithms. I'm not going to worry about the melting layer detection algorithm, but we talked a little bit about a bright banding. So here's the way that we kind of anticipate that. So we can use products that will actually show us where's the melting layer. If you were going to be trying to protect airplanes flying through icing conditions, you'd probably want to know that. This is what it looks like. So here we see, again, this is CC. We're looking at very consistent out here. So that's probably all snow. Very consistent in here. That's going to be rain. And in here, this area, this big yellow and green stuff, this is where it's inconsistent, right? That's lower cc. So this is inconsistent, saying you have both rain and snow existing. And then see this white ring? It's kind of here. This is where it is a little bit. This is where the radar is trying to say, hey, you know what? That's where the melting layer is. And so it says this is where the melting layer is, and it gives you the approximate height of that. Okay. Now, we can use all this information to classify hydrometeors, the hydrometeor for classification. So in other words, we are saying, well, gosh, knowing all these things about snow and ice and drop size and whether they're small or big drops, I'm going to let the computer figure out what it thinks it is. And it shows you this diagram. By the way, here's a supercell. If we look at the supercell, right, there's a little bit of a hook around here. So there's the hook. It's a nice looking storm. By the way, what's this? Right, the radar is probably up here. It's looking out through the core over here, and it says some three-body scatter spiked. This says, well, what do I think is going on? It's a program. It's a best guess. It says this red here, this red stuff is going to be hail. And then around it, we're going to get heavy rain. And then the light green is going to be rain. And then the yellow out here on the outskirts are going to be some of the big drops. So even in the hook, we've got maybe a little bit of hail, but we certainly have some rain and big drops around the size. And we are going to care about the big drops. Just so you know, we're going to be talking about that. Now, this is just an algorithm, right? We put inputs. Here's the values of reflectivity, of differential reflectivity, correlation coefficient, all these other things. They go into a computer and it tries to guess what it is. So according to this, it's going to say, well, gosh, this is a 78.9% chance that it's going to be heavy rain. With a 73.7% chance, it's hail. It'll show you heavy rain because that's the winner. That's the one that won. But do you understand it could have been hail, or it might be mixed in with hail? There's a 35% chance it's big drops. Could be some just lighter rain. You know, so these are all probability tables, so to speak. But since you have to, the VIP has to assign a color. It says, all right, the winner gets the color. And another caveat, things to be aware of, which is what caveat is, things to be careful of. You're looking high up. And so whatever it says it is here, it might say, hey, it's snow. Well, doesn't mean it's snowing on the ground, because where it's looking, it says it's snow. It certainly could go through the melting layer and turn into rain. So here's an example of that melting layer. Here's an RHI showing you the bright banding. Here's what it looks like on reflectivity, and you might see a little bit of it. It shows up on KDP pretty well, this weird stuff here. On ZDR, it shows up really nicely, and the best, remember we talked about correlation coefficient? That shows you really the best that we've got is in this ring here, and it tells you that's where the melting layer is. So it's more than just the bright band. You can actually use these products to help you find these things. So radar and the dual pole is a big improvement that's only been around for a few years. So we're really getting a little bit better at it, and it tells us some really cool things. So this is sort of a new technology. Non-meteorological targets. We've got maybe some precipitation up to the north toward Wisconsin. Up here, it's going to be high CC, and that tells us, well, it's probably raining. But over here, whatever this is near Glen Ellen, we're like, whoa, there's all sorts of weird colors in here, low CC. As it turns out, I believe that this was like locusts or grasshoppers. So they were flying around, and there was a big swarm of them showing up on radar, and we could tell that it wasn't rain. Here's some ones in South Florida. We're actually looking at some showers and thunderstorms, but we're looking at a lot of dusts and fires. So there's some fires out here that are creating some interesting pictures. Here's the changeover from rain to snow. Sometimes we want to know that. We see on radar, the reflectivity is just like, well, there's just stuff out there. But when we see this in CC, we are seeing an area where it's snow to the north, rain to the south, and this is the line over here as we go from rain here to snow up there, and that's the changeover. And obviously in the winter, we oftentimes want to know, well, it's supposed to start snowing when? This is a way that we can look at it. Now, the last thing, and this is really good for this class, we've talked a little bit about it, is we talked about the tornado debris ball. So here we're looking at reflectivity on the right, and we see the Hooke echo, right? Here's the Hooke echo. And in the Hooke echo, there's this very bright region right there. Okay, so that's like, wow, that's really big reflectivity. By the way, this is the Joplin tornado. When I go to velocity, I'm like, holy crap, look at that. That's maxed out delta V's gate to gate. So we're like, that's a tornado. And if you look here, it's like, why is the reflectivity so high in the tornado? And that's because it's picking up debris and it's being really reflective. But the best thing about it is I also want to use, I can use ZDR, but I definitely want to use CC. CC, correlation coefficient, says debris is going to be really inconsistent. And we see these big negative areas. Now that's exactly where the shear is gate to gate. It's where the Hooke echo is, but it's this thing here in combination with those other things, but this one especially, is where we go, that's a tornado debris signature. And if it's a tornado debris signature, that means it is a verified tornado. We've talked about how we need to add like investigations to figure out, is there a tornado with this? And we said there's BWERS and Hooke echoes and TVS and DRC, descending reflectivity core. The tornado debris signature is not a clue. It is a verification. It's like, okay, I just saw that guy pull the trigger. He's the gunman. So there we go. And that is a verified tornado. And it really comes in helpful. We're seeing a lot more tornadoes now that we may not have gotten reports because of this. So the Weather Service goes, I can see a tornado warning. Or I can see there's a tornado. I better have a warning out there. And they had a big tornado signature in Hattiesburg. I think this was just a slide that I had there that was supposed to play a video that does not play a video, but that's what the tornado debris signature is. And it's using this dual pole technology to get more information from the radar. So man, technology is awesome. We're getting better and better each year. So that's the end of the radar notes. The next time I'll see you guys will be over the next PowerPoint, which is PowerPoint 4, and we'll do that on multi-cell storms. Okay, guys, have a great day.